an esteemed researcher whose work at the intersection of neuroscience and quantum technology has significantly advanced our understanding and application of quantum sensors. Professor Pandey obtained his integrated MSc from IIT Bombay in chemistry, followed by a PhD from University of Chicago, where he delved into intricacies of nanoscale materials and their emergent physical properties. Currently, Professor Pandey's research is focused on exploring the unique behaviors of nanostructured materials, which diverge considerably from their bulk counterparts, offering unprecedented opportunities across various disciplines. So let's welcome Professor Anshu Pandey.
Thanks a lot for the very, very kind introduction. And I'll also thank all the volunteers who have set this whole thing up. Thank Quantum Research Park, and especially thank Srividya, Dr. Srividya, without whom, who's been putting up with all of us. So, okay, so there is a lot of uncertainty regarding my talk title, I realize, because somehow it has been changing from agenda to agenda. So now, at least for the people who are here and you are making a measurement, it was never about quantum sensors, it's actually about quantum dots and quantum with dots being more like it. So what my research group works on, as I was already introduced, I am at the solid state and structural chemistry unit, and what we work on are various sorts of nanocrystals. Our interests are, of course, development of photon sources, engineering various kinds of excitonic architectures, and also we do quite a bit of FT work on photo detection. Especially our interest areas are more towards longer wavelengths, which means towards the infrared. So telecom, infrared, in those areas. So yeah, so semiconductor quantum dots don't really need an introduction, because this year's chemistry did get a Nobel on exactly these objects. So for sake of brevity, these are essentially semiconductors which are trapped inside a micelle. So you have a soapy set of molecules over here surrounding a blob of central semiconductor. The central core of semiconductor, which is where all the fun properties lie, is incredibly tiny. It's this whole process, and at the same time this gives you materials which are of a very, very high quality indeed, which makes these so exciting for quantum applications. And these are very, very simple to process, which means anything you do with them would automatically get a lot of scalability. So that's really good. It doesn't stay at science level, it will be relatively simpler to translate to a technology. And the last thing is that these can be engineered to control physical properties, and that is where we are very big at, because this entire talk is entirely about this part, which is engineering materials to control their physical properties, and especially to address quantum applications, again leaning towards photonics. So what do I mean by engineering, and what all can we control? You'll be surprised by what all we can control. So I sort of refer back to our own old work, where we sort of were studying a class of nanocrystals. We won't worry too much about the chemical formulation of them, but let's talk about this term which is making up the y-axis. This says spontaneous lifetime. Now, given this audience, I would assume everyone here does know what a spontaneous lifetime means. It is a rather sacrosanct quantity. It is the rate at which a material would emit if you place it in vacuum, vacuum meaning here quantum vacuum, right? And that would be essentially a conversation happening between the vacuum and the material, assuming you have done nothing funny with the vacuum, which I promise you I haven't. Everything should be static, and you should get materials with just this property. Indeed, every other known material class has exactly this property. Its spontaneous lifetime is a sacrosanct quantity. It does not change, right? That's why it's measured. That's why it's a benchmark of properties of materials in some sense when we are talking about photonic properties. However, we were looking at this material and we realized there's something wrong with it. Its spontaneous lifetime evolves as a function of time. So again, I'm not doing anything funny like putting it in a cavity, changing the size of the cavity, nothing like that. This material is in free space, and what we find is, if we start trying to determine what its spontaneous lifetime is, it's changing. No, it's not superradiance, no, it's not lasing. It's something else, an intrinsic property of this material. This sort of motivated us to dig around a little deeper, and we wondered if this effect could be done on demand. Could we actually use this and get inspired by it and create materials where the spontaneous lifetime could be, tuned? Now you would again say, well, isn't that already done? Because that's what Purcell effect is about. So I'm not talking about the Purcell effect. The Purcell effect is when you take an emitter and you change the number of photonic density of state it has around it, and that allows you to sort of tune its spontaneous lifetime. This is not the Purcell effect I'm talking about. This material is again in free space. It's not inside a cavity, but it's doing it because its electronic structure is being engineered, wave functions are being engineered, and the electronic states are determining the spontaneous rate, not the vacuum. So as we change a certain compositional variable, we find that indeed the spontaneous emission lifetime changes. And in this case, this is a semi-log scale, so this is changing by 3 orders of magnitude, roughly. That's a lot. This would be challenging to do already with the Purcell effect. But again, as I promise you, there's no Purcell effect here. This is entirely wave function engineering being done at quantum dot level. So it provides you a massive, massive knob which you can turn at will and get essentially what you want out of your material. So that's really brilliant. So now let's talk about quantum dots in a more basic pedagogical sort of sense, which is what this talk is mostly about, discussing research from a simpler perspective. So where do quantum dots sit exactly? Just to give a quick introduction, we have on the extreme side of being really, really quantum, we have molecules. Molecules have very, very discrete energy levels, very sparse density of states. So, you know, if I have a highest occupied molecular orbital, a lowest unoccupied molecular orbital, and nothing in between. So molecules would seem like the most quantum objects of them all, except the problem is they have too much coupling to vibrations, which makes them a little less useful. So where you get this great splitting, you also get a few problems. If you talk about bulk semiconductors or bulk materials, you have a near continuous or continuous density of state, which again means, you know, you're not talking about quantum materials unless you're talking something out of Professor Srimantamite's talk. So now we are left with quantum dots in the middle, where you actually have quantum confinement, which means a density of state which is intermediate to molecules and bulk. The nice thing which happens at this level is, okay, you are not as quantum as a molecule, you are, you know, much more quantum than bulk, so you are somewhere stuck in between, but the point is you inherit good and bad properties, unfortunately, of both. The good property which you get out of bulk is that you get a lot of stability. The good properties you get out of molecules are quantum confinement, and you inherit the stability from bulk, which molecules don't have. So this gives you a material which has a lot of potential, and we are talking about their applications as quantum light emitters over here. So now that's a big word, quantum light emitter, and we can make it even bigger by looking at some of these application slides. Each one of these applications could merit 10 one-hour talks and still would barely scratch the surface of this. So I'm just throwing a few names out there. You have quantum cryptography, teleportation, computers, all of which stand to benefit or use a quantum emitter or quantum light somewhere in the middle of them. I cannot talk of any of them in the time given, and I don't intend to, but rather what I want to talk about is more elementary aspects. So let's first ask ourselves the simplest of questions, which unfortunately is also very, very misleading and disorienting. Let's ask ourselves, what is light exactly? Now, people would say, oh, I have already studied that. This is the first electrodynamics course. Light is Maxwell's equation, so it's a wave. That's fantastic. Then someone else comes along and says, no, light is not exactly a wave. It's particulate. It's made up of photons. So let's ask a slightly deeper, more insidious question. Is light classical or quantum? And what I mean by that, of course, everyone knows light is quantum. But let me ask it differently. I'm trying to ask if we know that, you know, photons are quanta of light, but is each photon in fact a quantum object? Now, what I'm trying to construct out of this thought experiment or this experiment which can be done in real life is that, you know, let's construct the simplest quantum experiment. And what will that be? We are just verifying that photons are quantum. What do I propose for my experiment? I say, well, I'm going to shine a laser at a Young's double slit type setup. What I'm going to get is, of course, everyone knows, you'll get an interferogram. There's nothing much complicated happening out here. Now, what I propose to do is, let me tune down this. So now over here what's happening, this is a show that classical light is in fact a wave, right? This is what Young's experiment did. Great. So I do what I like doing, which is tune down the laser intensity all the way till I, you know, do some calculations and find that approximately 1 photon on average will only be reaching the screen. And then I ask myself the question, so now, okay, great. Now on average only 1 photon gets to the screen at a time because my laser is really operating at low power. So I'm seeing individual light quanta. Now, let me ask ourselves, am I going to get the histogram back or not? So what is the answer? The right answer here is, we all know, yes indeed, you'll recover the interferogram. So now let me ask ourselves a slightly more insidious question. Great, so I recovered an interferogram. How exactly will I recover it? The detail of the experiment would be, I'll track it photon by photon. I'll have to sort of wait a long time So first one photon will arrive, I'll find it lands here, then another will arrive, it will land here, a third will arrive, it will go there. Eventually I'll be able to construct a histogram just by having many such events. And when I look at the shape of the histogram, I'll realize, oh good, it looks exactly like my interferogram did earlier. So then let me ask this question. From this experiment, am I able to conclude that I have just successfully done my simplest quantum science experiment with light? And does this prove to me that a photon is indeed a quantum object? Now we would rush to say yes, but in fact the sad answer is absolutely not. There's nothing quantum in this experiment at all. There's a bad reason for it, because let me do a verification. Let me verify what exactly was happening in this experiment. So I had my laser, which is running at very low power, and now what I do is let me put a beam splitter over here. Now there are easier and better ways to also conceive of this experiment, but I'm not going to do that because I want this beam splitter there for later use. So I'll put a beam splitter here. Great. And now what do I do? On this side, I put an instrument which is just counting the number of photons which are coming at a point of time. So what happens? Some of the photons will wind up here, others will go to the screen and produce this interferogram. I'll collect it for long enough and I'll know exactly what's happening. But this guy allows me to determine how many photons the laser is actually producing at a time. In this experiment, granted, there is a slight problem because I will not measure the photons which actually went there. Rather, I'll measure the photons which actually end up here. But with all due honesty, right, if the beam splitter works fine, if everything else is okay, as a matter of fact, this still makes sense. I'm still sampling 50% of the events here, and this gives me a very good idea of what sort of photon statistics is hitting this screen over here. And to my surprise, what I'll find is, even though my laser is tuned to generate an average of 1 photon at a time, in fact, lasers do not ever produce 1 photon at a time at low power. This never happens. What lasers produce is something called a Poisson distribution, right, named after the mathematician Poisson. And what this means is, you try to set the laser to give you 1 photon at a time. In fact, a lot of the time it gives you no photons. Some of the time it does give you a photon. At other times it will give you 2. Yet other times 3, 4, 5, and these are all bunched together in this very weird distribution termed as a Poisson distribution. So what exactly is going on? What does the Poisson distribution look like? You might still say, well, no, look, it will be peaked at 1. You are kind of correct. It will be sort of peaked at 1. But the trouble will still not leave you, because even when this distribution is peaked close to 1, the probability of having 2 photons at a time is only half of the probability of getting 1 photon. The probability of 3 photons is 1/6. So you're really going nowhere. And in fact, what you have collected is the property of still eminently classical light. It's still mostly consisting of photons which arrive together in packets. And then they sort of course, a packet of photons is classical. So it's going to interfere the way a classical wave does and hit the screen. So there's no real quantum science which happened over here. What is exactly going on? Why are we having this problem? Because when we are dealing with Poissonian statistics, the problem is uncertainty. The uncertainty in numbers of photon arrivals is related to the mean number of photons which are arriving, which means if you are trying to send 1 photon to the screen at a time, the uncertainty in getting 1 photon is almost equal to 1. And that means that a laser can never be your light source. What you want to do real quantum in general is to have less than 1 photon. You want to have the uncertainty less than the average number. That is when you can start saying, okay, now I'm doing some kind of quantum science here. So this would be the definition of non-classical light. This would be the definition of classical light. And what we are targeting is precisely this statistic here. So that is where single photon emission becomes an example of non-classical or quantum light, since the uncertainty associated with it ideally would go to 0. Right? The uncertainty in numbers of photons goes to 0, and that is what makes it a quantum kind of light. So a single photon in quantum mechanics would represent a quantum state, but whatever you are getting out of a laser, whether it is produced by stimulated emission or not, that's how a laser would work with stimulated emission. It's still not really any sort of quantum light. It's still all classical. So with that, let's sort of build up a few tools and see what quantum light sources and quantum light would be all about. So let's start off with this object, which is a beam splitter. I promise you I needed it for later, and here is where I'm going to need it. And let's set up this experiment, which consists of 2 detectors. So now this sounds like a lot of words and jargon. It is. But all this does is, this is just an overhyped kind of a stopwatch. What it does is, you have photons arriving from the sample. when one of the detectors is triggered, it starts the stopwatch, right? And it starts counting time. And when the second detector is triggered, it will again stop the stopwatch. And then all you look at is the interval between the start and stop times. This interval is used to generate this sort of a very ugly looking function called the G2 function, right? And this is just telling you, and I'll explain that in just a bit, that what is the probability of a photon arriving after a time tau if the first photon arrived at time t, right? So if photon 1 arrives here, what is the probability? I count tau seconds and then the next photon arrives, right? That's all it's trying to tell you. So it's basically an overbloated probability function, nothing more than that. And we are looking at the Poisson distribution. So this essentially looks slightly ugly. It is the n bar here represents the average number with which my light is shining. E raised to minus n is again negative of that average, and k factorial is, suppose I'll illustrate this in a bit more detail here. So now, suppose what is happening with this experiment, let's just see at time t, a photon arrives, like I mentioned, say at a detector 1, G2 tau will measure the probability that a second photon arrives at time tau later. So what we do in an actual experiment is we let the system run for a long period of time, we again build up a histogram of these events, and we get back this nice little function. And I'll suggest to you that this is actually the first measure of quantumness of light, which one could suggest. The first, not the only, but at least the first thing which you do. And good enough for today. So with that, let's try to again reconstruct our earlier thought experiment with a laser. This time I'll do one better. I'm going to use a pulse laser source. Alright, so earlier I was talking about a continuous laser and doing this with a laser pointer essentially. Now I'm not doing that. Now I'm talking about a pulse laser source, and this laser source is special. It generates an average of 1 photon in every pulse it produces. Fine. So what happens? The first thing which happens is, because the average number of photons is n bar in every pulse, so n bar is definitely equal to 1, right? That's very easy. We look up the Poisson distribution formula and ask ourselves, what is the probability that in a laser source, if the average number of photons arriving is 1, what is the probability of 0 photons arriving? The answer will be, well, just plug in 1 over here. K is 0 in this case because I'm looking at probability of 0 photons, so this is 0. And this is k factorial, 0 factorial is 1, so the long story short, the probability of getting 0 photons is just 1 over e. What is the probability of getting 1 photon? The answer is still 1 over e. What is the probability of getting 2 photons? As I had promised earlier, it is only half of the first, which is 1 over 2e. So what you see is, firstly, a Poisson distribution is really ugly. You try to set it to 1, you'll get 0 as equally often, and even worse, 2 is not very far away, right? It's pretty close. With that, let's see what G2 will do when you shine this sort of a light onto the system. Now, again, admittedly, this is an oversimplification. This is a bit of cheating because I'm not constructing a full histogram. I'm doing only the first step, but I've chosen this step very cleverly so that it allows us to recover the right answer. You know, if you choose it a little differently, you will get a wrong answer. So that's fine because this is only part of the answer. The rest of it will be constructed, but the final answer remains unchanged, right? So what now happens is the probability of one pulse triggering a single detector. So I'm looking at now a case where I have 2 pulses, all right, 2 successive pulses, and I'm examining this. So let's say, what is the probability that pulse 1 will trigger detector 1 and pulse 2 triggers yet another detector, one after the other. So what happens because of that? The pulses are arriving at an interval of tau. So the first pulse arrives, then the second pulse arrives. What is the probability that 1 triggers a detector, 2 also triggers a detector? The answer is, well, the probability, assuming everything is ideal, would be there is 1 photon in pulse 1 and another photon in pulse 2. What is the probability of that? That is 1 over e square, right? So in other words, your G2 function would be 1 over e times 1 over e, because P1 times P1, that's 1 over e square. That's easy enough. What is the probability now that, so what does this do, by the way? This produces a spike at tau, right? Because P1 times P1 is 1 over e square, which means that is the probability, and with that I get a peak amplitude of 1 over e square sitting precisely at tau, because it means pulse interval was tau, so I get a peak there, right? So that generates a side peak. Now what is the probability that pulse 1 triggers one of the detectors twice, or pulse 2 triggers the one of the detectors twice? That is only going to be the probability that 2 photons arrive in pulse 1, no photons in 0, or no photons in 0 and 2 in pulse 2. sorry, no photons in pulse 1 and both in pulse 2, or both photons in pulse 1, none in pulse 2. Probability of that, as you see quite clearly, is 1 over E times 1 over 2E in both the cases. So you get half E square in both cases, add them up and you get 1 over E square once again. What does this do? Because in this case, both the photons are arriving in the same pulse. Your tau in this case is 0, and what you get is a big tall spike in the middle. So what you get as a consequence of this, if you did this for a very long time, you would get a histogram where you get a tall spike at some time, then you get another tall spike at 0, then you get another tall spike at time tau, another tall spike at time 2 tau. You'll just keep on getting these sequence of tall spikes. And they'll all be of the identical height, and this is essentially a confirmation that this light is eminently classical. Now let's look at the simplest possible quantum light, or not the simplest possible, but one possible quantum light, which is an ideal single photon source, right? So what happens? Now, because this source is ideal and it is single photon, I can get rid of my Poisson function and rather consider what this source is going to do. So it's ideal. So at t equal to or 0, or sorry, the ideal means that every time it is asked for a pulse, it will only generate one photon. It cannot generate 0 ever, it cannot generate 2 ever, and it cannot generate any other number ever. What is the consequence of that? When I ask what is the probability that pulse 1 will trigger the detectors, pulse 2 will also trigger the detectors, the answer is P1 times P1, which is 1, because 1 times 1 is 1. What is probability of pulse 1 triggering detectors twice or pulse 2 triggering detectors twice? P2 times P0, P0 times P2. Either way, it doesn't matter because everything is 0 over here. So 0 times 0 is 0, 0 plus 0 is 0, which just gives me a 0. In other words, the probability of the 0 spike showing up is 0. The probability of this spike showing up is quite high, right? Or in fact is unity. So what I get therefore, if I construct a lot of these histograms, do a lot of these events and construct a histogram yet again, I'll get two tall spikes at tau and minus tau, but I'm going to get absolutely nothing here because it never happens that the same pulse triggers a detector twice. The consequence of that is I get absolutely nothing at 0, and this is an ideally quantum situation because I'm getting single photons out. So where does reality sit? Obviously reality will be somewhere in between pure classical and pure quantum. Reality sits where P0 is greater than 0, right? A real single photon source will never be quite as good as an ideal one, which means sometimes it will do nothing when light shines on it. Other times it will try to generate one photon, it will do it most of the time, but maybe not succeed all the time. So probability of 1 is less than 1, as close to 1 as it can get, but less than 1. Probability of 2 will also be there, unfortunately, because it's not ideal. The result is I'll get some sort of an average of what I'm supposed to get between classical and ideal, and I'll have a slight spike in the middle, but the major spikes will be right here. And this is easy to see again by doing this, that P1 times P1, because P1 is less than 1, so P1 is also less than 1, and because P2 and P0 are both non-zero now, so I'll still get an answer greater than 0, but you can see easily that the shorter the spike gets, the more and more quantum I'm getting. So that's how we see it. So what does a single photon source really have the job to do? The point is your light source is still the laser. It will generate a Poisson function, distribution of light. It's going to have some probability of giving you no photons, some probability of 1, 2, 3, 4, 5, etc., etc. The point is you'll firstly be driving the laser at pretty high power so that the probability of getting no photons out of the laser really vanishes or close to 0. And you're getting a large flux of photons. And then the job of the single photon source is to take in this Poisson input, convert it into a single quantum of output. So every time you get 5, 6, 10 photons into you, you simply refine it down to 1 photon and throw out that 1 photon, right? And the better you can do it, the better you get. So what are the sorts of single photon sources out there? There's a huge library of them. The one which is the most different from all of them, and none of what I've been talking about really applies to, are photon down conversion generated single photon sources. These are fantastic, these are simple to set up with one problem, that they do not work when you want them to. They have a probabilistic temporal property, which means they can generate single photons very nicely, but at intervals of time which are indeterminate. And that is where they have a weakness. You have single molecular materials, you have nitrogen vacancy centers, 2D materials. They all come with their own quirks, some of which are good, some of which are bad. Molecules can photo bleach. Finding defects is hard, and defects are also coupled to vibrations. So there are all kinds of issues coming in all of these materials. The workhorse, the other workhorse other than photon down conversion is epitaxial quantum dots. Over here the problem once again is that these are, not all identical. So spatially there will be a spread of properties. Spectral properties will vary from dot to dot very slightly, but at the same time these are remarkably robust and stable. These are very good sources, but the trouble with them is they are not quite very scalable. They are very expensive to make, and it's very experimentally demanding to actually make them. So against this backdrop, colloidal dots seem really, really good because they are easier to make relatively in terms of the infrastructure which goes in. And it sounds that if you could get single photons out of them, you would have a very, very scalable substrate indeed. So this all sounds fantastic, but is it really true? The answer is no. If it was this easy, then in that case, there would be nothing to talk about. The trouble with colloidal quantum dots now, which is the entire focus of this talk, is that luminescence in these materials is not permanent. It keeps going on and off continuously, right? This switching, so you take a single quantum dot, you start shining laser light on it, and you'll find that, okay, it emits, then it doesn't emit, it emits, then it doesn't emit. You'd think, okay, maybe I'm just seeing the Poisson distribution coming out from the laser. The answer is absolutely not. There's actually, the laser is being tuned at a very high power, so laser is shining photons continuously, but the trouble is the quantum dot decides randomly when to switch on and off for no reason. And this follows a very ugly sort of a statistic which is called a power law. I call it ugly in the context of quantum. It's very beautiful in other contexts, but in this context it's really undesirable. And here you really don't want power laws type statistics at all. And this means that this seemingly would render quantum dots totally unusable. Except that people have acknowledged this problem and have been working on it for a very long time. And now at least we understand, or we have a fair idea of what is going on. So at least the school of thought which I come from, this switch on, switch off business is happening because, okay, a quantum dot is nice and ideal, sort of a round piece of semiconductor, but at some point of time when you shine enough light, you activate a recombination center inside. And the outcome of that is, once you do get a recombination center in the quantum dot, your excitons recombine there, and the consequence of that would be that there will be no further emission from the quantum dot. This could be anything. This could be elemental cadmium, elemental selenium. We don't know what it is, but at the same time it's clear that these keep appearing and disappearing seemingly at random, and that's what's driving the quantum dot in this on-off behavior. What is the solution for it? The solution for it was discovered by many researchers have done a lot of work on it. Solution, of course, is to just have more resilient surfaces, and there's some really splendid work on this subject done by the groups of Benoit Dubatry, Victor Clément, Monji Pavendi, all of whom were able to successfully show that you could suppress deep traps completely, and the result of it is that you get a very, very nice stable power output from a quantum dot. So in this case, the quantum dot is behaving like a true single photon emitter, right? And it's a very good quality one. It's not blinking at all. So this sounds very good. So you'll say, okay, that was a quick end to the talk, but unfortunately, there's still more. The second trouble is you have to start scratching your head. Why is a quantum dot a single photon emitter in the first place? It's not an easy question to answer, because if you look at the electronic structure of a quantum dot, okay, let's leave the intricacies aside. Let's just see what exactly can populate the lowest lying excited states of a quantum dot. The answer is it can be populated by two nearly degenerate excitons. Not one, mind you, but by two. And therein lies a problem. Because you suddenly realize, okay, I would have thought that if I had only one exciton inside a quantum dot, it would make for a very good quantum emitter. But the trouble is, it can be populated by two. So if my laser is shining really hard, I suddenly have two excitons there and both can emit. And that's a problem. So quantum dots, in other words, need a scheme for multi-exciton rejection. So if you get more than two excitons ever inside a quantum dot, they need to have a mechanism by which they can kill one of the excitons so that only one of them survives for the emission event. And the most commonly used such mechanism would be Auger-based annihilation of multi-excitons. So if you have two of them, you want to kill off one of them and get only one back. So what does Auger look like? It looks essentially like this animation over here. So let's play that all over again. What you have initially started off from is a bi-exciton, which is two excitons, right? Now, in my case, what happens is after some time, I press the slide button, one of the excitons relaxes, the other one is kicked high, and then it relaxes back down to the band edge thermally. So now I get, out of two, I get one exciton, and this will of course emit as a single exciton from this point on. And the faster this process occurs, the neater and cleaner and tidier would my emission be. Now, very approximately, while this in fact is an electron-electron collision process, very approximately one can think of this as an energy transfer as well. Now, experts would rush and say that no, it cannot be, but well, there is an approximation which this does work out as an energy transfer, which is if there is anything which breaks the symmetry of a quantum dot, which happens more often than not. In this case, one can think of it as an interband energy transfer from an interband transition into an intraband transition. Intraband meaning it's going within the conduction band, interband meaning it's falling to across the band from conduction to valence. So now this would seem okay if this is simple and done, then in that case again you have an answer, but the answer is not very good here. The problem is intraband transitions have been studied a lot, and it is very well known by this excellent work by Heinz and Giosione that 99% of the total oscillator strength of intraband transitions is in the 1s/1p transition over here, and only 1% gets distributed among the rest of the transitions. What does this number mean? It means 1s/1p sits very low in energy as a matter of fact, and the electron is being kicked up to some very high lying state. As a matter of fact, this transition is very weak indeed. And if I'm talking about it as an energy transfer, it's in fact going to be really improbable for this to happen. That's not an optimal situation, and this ensures that ordinary quantum dots have very low rates of multi-exciton recombination, sometimes something which you would not desire. So what exactly happens, and why is this relevant? I've already alluded why it's relevant. Because you could say that, oh well, I'll just get a better G2 by running my laser at low powers, so I'm only generating one electron most of the time. But the trouble is you will still have Poisson tails. They will still generate 2, 3, 4 excitons with some probability. Having this is not a solution, and when you do get them, your quantum dot will not be ready to be a very good quantum emitter. And in real life, you actually want to drive the quantum dot really hard so that you don't have this probability of 0 from the laser. And that means that your quantum dot has to equip itself to deal with the other excitations. And that means that this transition, which has gone really weak, as drawn here, so this is the 1s to a very higher lying transition, this needs to be strengthened, and the only place where it's going to gain its strength is if this transition from the 1s/1p becomes progressively weaker. So how do you do that? And first of all, let's see how it exactly works out. This is how it works. If I have a quantum dot like cadmium selenide, cadmium sulfide, so what happens now, which is the state of the art of the state of the art, because this thing doesn't blink at all. In that case, what you find is at very low laser powers, you get an emission pattern which sort of looks like this. So this is again the G2 shown over here. Please don't mind the extra spikes here. All you're worried about is that the central spike has a certain height. We remember that this should have ideally been 0. It's not. And this other peak is quite a bit higher than that. So this is really quantum right now as it is. But as I ramp up power, this dot quickly changes and starts behaving quite classically indeed. Right? So now it's no longer arguably a quantum object, it's in fact getting quite a bit more classical. So the result of it is that this dot, for all its good properties, is not enough as a quantum emitter. What is the solution? What we decided to attack the problem with is engineering wave functions once again, and trying to see if we could restrict the 1s/1p oscillator strength and thereby cause this materials family to do a bit more than it normally does. The specific question which we asked was ourselves, can hollow wave functions help? Now this is a bit hard to visualize. Normally the 1s state of a quantum dot is like a big spherical ball. What I am talking about now by a hollow thing is not a toroid or a some kind of a other shape, but rather what I am trying to talk about here is in fact a hollow shell, right? So imagine a rubber ball, but there's nothing in the rubber ball other than the outer surface. So that's sort of a wave function. Would that help a little bit? And can we actually build it? So the answer would be, of course, it's easy to see how to build such a wave function. To build it, you would say, okay, take a drill, scoop out the center of the dot, leave the rest of it there, and essentially presto, there you go, you now have a hollow wave function. Yes, but very hard to do in practice. But why would it even work? Why are we even thinking like that? The answer is easy to see. if you see the problem, why this transition is so weak, the answer is because this S state is spread out over the whole dot and not very oscillatory. But if you look at the higher wave functions, they get actually very oscillatory indeed. So when you have a non-oscillatory state trying to go into a very oscillatory state, the overlaps, spectroscopically speaking, the transition probabilities always get very, very poor, right? So you can't really do this. Now, when you start talking, however, about this hollow structure, what exactly is going to happen? In this case, well, the hollow region, I assume, does not obstruct this very highly excited state, but the S state certainly is going to get awfully squeezed. The outcome of this is that when the S state is very tiny, you see that all of a sudden, it does not feel that this state is so oscillatory anymore, because all it sees is a tiny fragment of this state, and the state looks just fine to it, right? So now the S state can actually transition into it much more strongly than it was doing earlier, right? So I have essentially borrowed a lot of the oscillator strength from the T-like level and dumped it into this level, and that is ideally what I want, because now all of a sudden I'll be able to have a much higher rate of recombination. So can you actually do that? Can you scoop out the center of the dot and make something magical like that? Answer is no. You can't do that, but you can do something simpler, which is take a very wide gap semiconductor, in this case zinc sulfide, dump it in the middle of the dot, and this has the same effect, because now the S state will sort of expand out here, while the higher lying states will still sit up here, and you achieve essentially the same effect. So does this effect really work? Is this really a trick which is truly worth it? The answer happens to be yes. The reason is because if we now construct a dot with this sort of a central place where nothing can go in other than the very excited states, while the lower lying states sort of spread out to the edge, in that case what you do get is you get a very nice G2 indeed. But what is even nicer is as you ramp up power, the G2 doesn't really rise up. The material stays extremely quantum for quite of the powers that you are doing, and which means you can now excite this at very high fluences. You can ensure that you are always creating electron hole pairs in the system. It's always populated, it's going to respond to every single laser pulse, and at the same time it's going to respond with a very high probability of generating a single photon. So what we get as an outcome, which is out here from my group, which is, you sort of get a quantum dot based single photon source which works at very high pump pass. So this work is out, and also interesting from the technological viewpoint, so we are pursuing those as well. So I have tried to cover challenges and describe some solutions to how solution process dots can be used as emitters. I'll thank the people who have done all the work. So most of this talk concerned work of Parna Roy with very good inputs from Preetha and some from Parinita as well. And I thank Quantum Research Park, Government of Karnataka, and thank you of course for your attention. So I'll answer questions if any, if there is time. Sessions? Questions? Yes.
In the wave function follow that is it possible like if any potential is applied, like a barrier potential or a finite well potential, is it possible to bring out that hollow wave function?
Sorry, could you explain here? Maybe I'll go here. This is a good slide for it. Yeah. What are you trying to do? So you want to bring the this guy down here? Sorry?
No, sir, in the previous slide where
previous slide?
Yes.
This one. Yes. So when I say hollow wave function, I mean that the ground state is sort of occupying this shell-like space. So ground state is now like a shell. The excited states are still going to be smudged out in all space. Okay, that's the ideal situation, because excited state, even though the detail won't show it, will be a highly oscillatory state. But by making the ground state so thin, the point is that it's going to overlap with only a single oscillation of the excited state. And that means, what happens in these transition dipole moments, integrals, is that when you are having a state like this overlap with a highly oscillatory state, it's a bit like taking a Fourier transform. The problem is one half of the first transition will clash or cancel off with quite a bit of the next, will cancel off with the next phase of the integral. So the net integral falls to a very low value, only because one part of it may be very large, but the next part of it makes a negative contribution which is equally large. So they cancel off. The point is, however, if I go to such a situation, right, I have killed off the rest of the integrals. So only one small tiny part of the transition dipole integral survives in this case. I'm still integrating over all thing, but I've pushed my ground state wave function down to 0. The outcome of that is precisely shown over here, that earlier I was sampling this whole thing. So whatever I get here will be cancelled off in part by here, in part by here, and I get a very low number. Now, you don't have to worry about the middle part at all. I get something from here, but then there's nothing to cancel it off. That's gone. Right? This guy was killing off most of it, this integral with this middle hump was killing off most of it, but the middle hump is gone over here. So this part of the integral is now dropping to 0. The result is what is left of it is much stronger. Right? So that's sort of the idea.
So is the middle hump, is it like a barrier potential?
So I have used a barrier potential to kill off the middle part of the wave function in the ground state. Right? That's exactly what I have done. Yeah.
Thank you, sir.
So again, it's not talking about humps being engineered, it's talking about wave functions being engineered. More? Great, then done? No more questions? Wonderful.
I would like to thank the professor for his wonderful talk, and I would request professors to accept this small token of appreciation.